hundreds of millions of years before dinosaurs. Earth was a very different planet. Most of the surface was ocean, and complex life was concentrated almost entirely beneath the waves. The seas were filled with forms so unfamiliar that modern ecosystems would feel surprisingly familiar by comparison. Then Earth entered one of the earliest major biodiversity crises in recorded geological history. It unfolded in two phases, a strong cooling interval followed later by a rapid warming shift. Together, these changes reshaped marine ecosystems on a global scale. Scientists call this event the Late Ordovician mass extinction. It occurred around 445 million years ago and is often described as the first of the Big Five mass extinctions, periods when biodiversity declined faster than ecosystems could naturally replace it. Across Earth's long history, life has not only evolved, it has also been interrupted by major turning points. These events were not random in their impact. When environments shift quickly, even stable ecosystems can change dramatically in a relatively short geological span. To understand why this event mattered, we must first imagine Earth before it happened. During the Ordovician, land was mostly barren. Plants were primitive, simple, and low to the ground. But under the sea, biodiversity surged in what scientists call one of the greatest expansions of marine life in Earth's history. Sea levels were far higher than today, flooding large parts of continental margins. Warm seas covered shallow shelves, creating enormous habitats where marine communities could diversify and spread. Reef systems expanded and supported dense networks of life. But many animals of this time looked unfamiliar. Trilobites across the seafloor, early coral communities, armored invertebrates, and unusual swimming species that filled nearly every marine niche. Some of the largest hunters of the era were long-shelled cephalopods, relatives of modern squids and octopuses, protected by extended tubular shells. Their silhouettes likely moved through the water like slow, controlled shadows. Trilobites were among the most recognizable animals of the Paleozoic. They existed in huge variety and occupied many habitats, from shallow coastal waters to deeper environments. Their success made them a key part of the Ordovician marine world. Other groups included sea scorpions, early jawless fish, and conodonts, small animals known today mainly from tiny tooth-like fossils. Together, these organisms formed an ecosystem that was complex, productive, and stable for millions of years. But stability can be fragile. Around 445 million years ago, Earth began shifting toward cooler conditions. Gondwana, a massive southern landmass, moved closer to polar latitudes. Cooling likely involved multiple influences, including atmospheric changes and ocean circulation shifts. Large ice sheets formed across parts of the southern hemisphere. As more water became stored as ice, sea levels fell significantly. Shallow marine habitats, where much of Ordovician life lived, shrunk quickly, reducing space and stability for many communities. Cooling also altered ocean circulation. When water layers mix less effectively, oxygen distribution can change, especially in deeper regions. Evidence from sediments suggests that some marine environments became harder to inhabit, especially for organisms adapted to consistent conditions. This was the first major phase of biodiversity decline. Many groups that depended on broad, shallow shelves struggled as habitats shifted. The marine world became simpler, with fewer dominant reef communities and fewer large, specialized forms. After this initial decline, ecosystems did not fully collapse into emptiness. Instead, a new set of communities adapted to cooler conditions. These organisms tended to be smaller and more flexible, better suited to environments with rapid changes in temperature, depth, and nutrients. Then came the second phase. As the climate shifted again and glaciers retreated, sea levels rose. Habitats changed rapidly in the opposite direction. Some communities adapted to cooler, shallower settings, found their environment transformed faster than they could adjust. This second shift intensified environmental stress across wide areas. Changes in circulation and nutrients likely influenced oxygen levels and food availability. The combined result was a major restructuring of marine biodiversity, one that left a clear boundary in the fossil record. By the end of the Late Ordovician event, a large portion of marine species had disappeared, and many surviving lineages were reduced in diversity. Some groups never returned to their earlier dominance. Others became the foundation for the next chapter of life in the Silurian period. Recovery took time. Ecosystems had to rebuild food webs, habitats, and stability, but life persisted. Over millions of years, the marine communities reorganized and prepared the stage for major evolutionary developments, including the later rise of fishes in subsequent periods. The Late Ordovician extinction is not as famous as the event linked to the end of the dinosaurs, but it was one of the earliest global turning points in complex life. Its cause is still debated, but its signature is clear. Rapid environmental change can reshape the living world. In Earth's rock layers, this story remains preserved, waiting to be read.